Something a little bit different this time. We're going to have a look at an asteroid that's been given the name Bennu, which is derived from a mythological Egyptian bird. And so, in fact, all of the features that have been discovered on the surface of Bennu are named after various birds. So Bennu was first discovered in 1999, and it was realized very rapidly that it was a NEO, a near-Earth object coming close to the Earth every 6 years. And the animation there is a Goldstone radar image of Bennu. It's not a particularly high resolution, but it was the first attempt at trying to understand this relatively small asteroid. From the data and the animation and further study, they were able to produce a model of the shape of this asteroid, which is quite interesting. It almost looks like it's cubic, doesn't it, as it rotates there? And it's certainly fatter around its equatorial ridge there than at the poles. So that was the image derived from radar studies. But actually, when we sent a spacecraft there, we found this, which confirms that they pretty much got it right. This shows Bennu rotating every 4.9 hours, and they were able to see a couple of things from this. Firstly, it's getting faster. It's gradually spinning up more quickly by 1 second every 100 years. So not a very great rapid increase, but an increase nonetheless. And that's powered by the effect of the heat from the sun and perhaps by the gradual shrinkage of Bennu, rather like a figure skater on ice who rotates and pulls their arms in and goes into a faster spin. But what I love about this animation are the giant boulders that you can see on the surface here. And this is a real image, it's not an artist's impression, of just what a rubble pile Bennu is and how individual extra rocks have sort of landed on the surface. You can imagine the one that's going around in the middle there previously having been orbiting for some time and gradually spiraled in until it's just sat on the surface. So fascinating to see that. Now, Bennu itself, it's not particularly big, 500 meters in diameter. That doesn't sound like much, but it's enough that it weighs 1 billion tons. And when you work out from the size and the mass of the object, you find the density, and it's less dense overall than water. So there's probably a lot of voids inside here. There's very little gravity holding it together. So there's no reason for the gaps between all those lumps of rubble to be squeezed out. And so there's probably a lot of holes inside the material. That material seems to be very carbon rich. It's a carbonaceous C-type asteroid, C for carbon, and very, very dark in color. I mean, the picture makes it look quite bright, but really this is a near black, and they've had to wind the contrast up to make this picture. And C-type asteroids are generally found further out in the outer parts of the asteroid belt, rather than in the inner solar system coming into the region of the Earth. So quite strange. Now, some people have also made suggestions that maybe it's not just low density, but hollow. And of course, that's brought people out saying, oh, Bennu's an alien spacecraft. Doesn't look like one to me, really. That 500-meter diameter, 550 to be precise, across the equatorial direction, is a lot bigger, though, than the meteor that exploded over Chelyabinsk about 10 years ago and broke a whole lot of windows and sent flying glass and injured a few people. And I've actually got a fragment of the Chelyabinsk meteor in my collection. But Bennu, a whole different story, much bigger. So something we need to perhaps worry about in terms of near-Earth orbits. And talking of orbits, here's a little plot of that orbit showing how it crosses the Earth's orbit. In fact, shown crossing twice a year, but of course there's a slight tilt, so one of those is a much closer approach than the other. And in fact intersects the orbit of Mars as well. So it's one of these bodies that is potentially held in a orbital lock by crossing with 2 planets, and we see that in a number of objects in the solar system. So I say it crosses the orbit, and in fact in 2060 we've got this little animation of this purple track of Bennu from the Earth's point of view. So we're holding the Earth, the blue dot in the middle, still, and if you do that, then the orbit of Bennu looks like this rather crazy purple line, and you can see how it comes very close to us. Quite a close approach there, and then later on an even closer approach. So here it comes round again, spiraling closer to us, and there is the close approach that it's going to make. So quite fascinating. And when it does so, this will be 120% of the moon's distance from the Earth, so not dangerous at that distance, not really any chance of it hitting. Looks a bit like it on the picture, doesn't it? And at that size, 500 meters across, it'll be too dim to see, so not the most spectacular event. But we are worried about this meteor, this asteroid, in the long run, because when we trace those repeated crossings, there's one in 2031, which brings it much closer than the moon, in fact 65,000 miles, so only twice as far away really as many of our communication satellites, maybe 3 times as far, something like that, but a lot less distant than the 300,000 miles that it is out to lunar orbit. So quite dangerous. 2175, it comes by again, and all these passes are on the 25th of September. That's the date at which those orbits intersect. So we are crossing Bennu's orbit on the 25th of September, and it just so happens that on these particular years, Bennu will be in that part of its orbit at the time. Now, it's a 1 in 24,000 chance that that will actually hit the Earth at that point. That's pretty remote, and anything below about 1% we tend to not be too concerned about, although these things do need watching. But if you add up all the close approaches over the next 200 years, that the odds of that making an impact drop to 1 in 2,700. And the reason that we would worry about this is because, in fact, it's quite difficult to predict the orbits of asteroids. What happens is that they are orbiting, they should behave perfectly normally and be controlled by gravity, you would think, but the heat from the sun plays a part as well. Because these bodies are relatively small, what happens is that the sun's heat hits one side of the asteroid and heats it up, and then the asteroid rotates around, taking that warmed side away from the direct sunlight, and it starts radiating that heat out into the cold of space as infrared light, and that creates a slight thrust. So you have a heated sunward side, a warm side that's recently been heated, and then it's colder on the reverse side, and the side that is essentially dawn for the satellite. And so there is a thrust away from the sun created by the radiation pressure, and a thrust laterally because the sunset side is warmer than the sunrise side. And so the infrared radiation gives it a little bit of a push. And of course, what happens depends on which way round the body is rotating. And so this so-called Yarkovsky effect tends to cause asteroids to wander off the perfectly elliptical path, even after allowing for all the perturbing effects of the planets. And so making predictions into the future is quite difficult. And so, given that this has this chance of coming our way, and that it might one day hit the Earth, it was decided that we would send a spacecraft, and the OSIRIS-REx mission was dedicated to this task. Named after a mythological bird, as I said, OSIRIS-REx looks a bit like a heron there in the picture, so they tell me, with the wings of the solar panel. So the spacecraft was launched and set off towards us, Bennu, and here's the first image from its onboard cameras. The green circle's been added, tracking the movement of its target across the star field there. So it was gradually homing in. As it approached Bennu, one of the images that it took was this one, showing quite a reasonable image of the rocky surface of Bennu and lots of small fragments, as if Bennu was shooting rocks out in the direction of the spacecraft. And this was a little bit of a surprise, and leads to underpinning something which was suspected for a while, which is that as we cross the September the 25th orbit crossing, creates a minor meteor shower. Small fragments of Bennu that have been ejected from it seem to fall into our atmosphere, and the Earth sweeps them up as it goes round, and it creates a minor meteor shower. Now, this is not one to go outside and target, because I think the ZHR, the zenith hourly rate, the number of meteors per hour, is 1, whereas some of the really big meteor showers, it's more like 100. So you might be able to identify a meteor, but there are a number of random meteors anyway. But the point is that there are fragments of Bennu coming to Earth already from that orbital crossing. Here's another fantastic picture showing that rubble pile composition with boulders sort of 60 meters across, that sort of size. And at the bottom there, the ridge, this equatorial ridge sticking out slightly. And we see that on a number of bodies in the solar system. We'll look at those later, perhaps in another talk. But as they approached, they were looking to see where they would actually touch down, and they were choosing a number of possible landing sites. There are some shots here of some of the landing sites on the northern hemisphere, just taken from just over a mile, 1.8 kilometers above the surface. They're showing places that they could potentially aim for to go and touch down and grab a sample to bring home. And in 2020, on the 20th of October, we received this image series back of the probe of the lander descending onto the surface. And you can see as it makes contact, here we go, it kicks up a whole lot of fragments, and then the spacecraft rather rebounded off the surface. This was planned. It wasn't aiming to touch down and stay there. And it went in with the lid of its collecting container open, with the aim of dislodging a whole load of fragments and collecting some of them into the container. So here's an image of it actually at the moment of impact there. And the idea was to try and get about 60 grams of material. But in the end, it actually managed to pick up a whole kilogram. So did very much better at collecting fragments than was planned. Although there was some difficulty with the spacecraft. They couldn't get the lid shut on the container for a while. But eventually that was all sorted out, and the fragments were locked away, ready to bring back to the Earth. One of the things they noticed on the surface from some of these detailed images was a number of bright grains that are here, and these appear to be pyroxene minerals, and we believe these are fragments of Vesta. We have a number of fragments of the asteroid Vesta here on Earth. There's a massive crater on the nose of Vesta, the Rio Silva crater, and possibly almost large enough of an impact that made that crater to have nearly destroyed Vesta. It's created a vast shower of fragments, many of which have landed on the Earth, a very, very common type of meteorite, in fact. And here is further evidence of that impact, with fragments of one asteroid having landed on the surface of another. So what of the results? Well, one of the results that was soon discovered from the spacecraft as it approached Bennu was water. The spectrometer was able to reveal the infrared spectrum of there being quite a lot of water molecules present. So much so, in fact, that we think about 1% of the total mass of Bennu, that billion tons, is water. so 10 million tons of water approximately. Most of it's locked up in hydration of minerals. There are minerals called phyllosilicates, metals with silicon oxides and water, and these seem to have locked up quite a lot of the water, but some of it's probably there as ice, and there might even be pockets of water trapped in some of the voids inside. Now, water, we've got a lot of water on Earth, but having water available in space, somewhere where the gravity is very low, could be an excellent place to go and retrieve this water, reprocess the material, extract the H2O, and use it as water, or split it into hydrogen and oxygen for the use of further rocket fuel. So we could end up with Bennu being somewhere that there's a fuel station in space for future spacecraft, probably a long time into the future, that one. So OSIRIS-REx headed back to Earth armed with its kilogram of Bennu dust, and didn't land, but it dropped a capsule, and here's the capsule, landed in September of 2023 in the Utah desert. I mean, it used the fact that Bennu's orbit with which it was co-traveling crosses the Earth's orbit in September, hence the date, but it was able to nicely land, and here's the container opened with the Bennu dust in it in the central part of the image there, and then on the right we've got some microscope images of some of the grains. The material's been distributed to many labs over the past 18 months or so, all around the world, for a whole host of different analysis to be carried out. Now, one of the things that was found was, again, confirmation of a lot of this water, and quite a lot of it was in the presence of hydrated carbonate minerals, veins of white, bright material running through the rest of the asteroid, some of them as thick as 6 inches wide and 1 meter long. And these carbonates must have formed in hot, warm water. They just don't form, these hydrated carbonate materials, anywhere else. We find these in the geological record on the Earth, and it's evidence of a warm, wet period when you find things like cap carbonate rocks and so forth. So now this is interesting because Bennu itself is too small, really, to have been able to reach a temperature that would have created these minerals, and it suggests that they were formed elsewhere. And the theory goes that perhaps Bennu was part of a larger object in the past. And this makes some sense because of its location and the fact that we don't tend to find this type of asteroid in orbit close in the inner part of the solar system. These C-type carbonaceous asteroids tend to be further out. So it's likely, and some of the dating of the materials, the last time they were melted and so forth, confirms that probably 700 million years ago, some people say a bit further back, maybe 2,000 million years ago, but I tend to go with the 700 million years on the body of evidence that there is. This seems to have been a collision between two baby planets, two planetesimals, two large asteroids, whatever you want to call them, out in the asteroid belt. And a number of fragments, many small ones and some large ones, were created as the impact ripped a larger parent body apart. And it was probably on that parent body where it was large enough and warm enough as a result of trapping all the heat of formation and the radioactive nucleotides to have liquid water and warm liquid water running through the veins inside the rock and creating those carbonates, the hydrated carbonate materials. So that collision broke up the larger parent body and sent Bennu into an orbit that it's now in, controlled by Mars and the Earth in terms of gravitational lock. But it also probably created a number of other larger asteroids. And there are three particular ones in cases in point, Nysa, Polana, and Eulalia. And these are really much, much bigger, 1,000 times the size of Bennu. So we've got 113 kilometers for Nysa, Polana 55, and Eulalia 19 kilometers. So Bennu is only half a kilometer, remember, 500 meters. So these are the big members of this family, and they probably all came from the destruction of a larger object out there in the outer reaches of the asteroid belt. There's also asteroid Ryugu, which looks very similar to Bennu. That was visited by a different spacecraft, the Hayabusa 2 spacecraft from Japan. So it's interesting to see that these objects are there and were further out in the solar system when they were born, and then broken up. But the real interesting fact that has only come out in January of 2025, which was leading me to make this talk at all, was the fact that the results from the chemical analysis at labs around the world are showing that we can detect 14 of the 20 amino acids that make up the proteins of all living things on Earth in the material in Bennu. Now, we've known that amino acids have been found in meteorites and so forth, but this is a very large collection, and to find 14 out of 20 of the important amino acids pre-existing in these bodies that have come from the asteroid belt is fascinating. But even more fascinating, we have found all 5 of the A, T, C, G, and U nucleotide bases, the nitrogen-containing aromatics that make up the core of DNA or RNA and code by their sequence for the whole of life as we know it. And so it seems extraordinarily likely that the Earth has been bombarded by fragments of these asteroids. We're still seeing occasional meteors in September as part of that, as I've already said. And it seems that that's probably been going on since the dawn of the solar system, and maybe that the seeds of life came to the Earth from these bodies out there, and possibly from this destroyed baby planet in the outer part of the asteroid belt region, a little bit further from the sun, where conditions were just right to cook up the initial organic soup. And maybe the brines of Bennu are where the broth of life with the building blocks fell to Earth back then 4,000 million years ago and kicked everything off. Wouldn't that be interesting? It'd be very, very difficult to be certain about something like this, but the thing I love about this subject is all these connections and the possibilities which just beg further investigation. So thanks very much for listening, and I hope you've enjoyed that whistle-stop tour around the asteroid Bennu.